You're back, and I hope you enjoyed your breakfast, lunch, or dinner, and I hope it holds to the same standard as we usually have each year here in Santa Barbara. And just a quick reminder for anyone else new join us, we're now going to show a short version of the talk, followed by a Q&A session. There is a longer, more detailed version of the talk available on YouTube if you want to hear more details. And if you want to ask questions, you can either do it here in the Zoom or in the chat room via Zulip, which you can access from the workshop website. Okay, so welcome to the third session of attacks on cryptography. This is the election security session, and we're going to hear about weaknesses in the Moskva internet voting system. The talk will be given by Pierrick Gaudry. So Matej, can you start the video?
This talk is about Moscow internet voting system that was used about 1 year ago for an election that I'm going to describe a bit. And this is joint work with Alexander Golovnev and special thanks to Julia Krivonozova, who advertised the existence of public testing for this voting, the e-voting community. So what kind of election are we talking about? So it was about 1 year ago, maybe you remember, it was a day of local elections in Russia, and especially in Moscow, election of the city parliament. It's called Moskva Duma. And there are 45 districts, each of them having one representative in this parliament, and each of them have about the same number of voters. And the rules are pretty simple in each district. First past the post, maybe the candidate with the largest number of votes gets seats. In the 3 districts, an internet voting experiment was proposed. Any voter could register and use internet voting, and the software that was used for that was made public, at least partly, on GitHub, and the public testing was organized with bounty programs associated to it. If you remember, last summer, it was not exactly a peaceful context. Several protests occurred just precisely for this election due to rejection of opposition candidacies, and with thousands of people and participants to these protests. And so this was kind of weird time where they wanted to test a new internet system, and in a very weird, difficult context. And they published the source code for testing only 2 months, even less than 2 months before the real election. Shortly thereafter, Julia Krivonozova published a blog post really advertising this public testing that was going on in Russia with everything written in Russian. So the blog post was written in English, and it was advertised in the e-voting community. And that's from there that I heard about that. And it was summer, so there was some vacation, blah, blah, blah. But at some point I discovered some attacks on the encryption scheme. And they had to update the system, taking my remark into account. But shortly after, Alexander found another attack, and then, as you can imagine, only a few weeks before the D-Day, started to become chaotic. But and the last update was only 2 days before the election. So the message here is that everything is very stretched. In only less than 2 months, a lot occurred, and in a context that was not exactly simple. So that's the timeline, and now I'm going to describe a bit more what they had in their encryption scheme at the beginning. So they used some kind of triple El-Gamal encryption, something that they called multi-level El-Gamal. I had never heard of it before, so it looked very suspicious. And actually, it's a very bad idea that I'm going to show. So the idea is just to have 3 settings for El-Gamal encryption in Z over PZ with safe primes. And the keys is just a concatenation of the secret keys and public keys from these 3 groups. And encryption of message, the first group is just you encrypt the message. You get a pair of group element as a ciphertext. And then you take one part that is going to become part of the final ciphertext, and the other part you encrypt it again with the second group setting, and then you do it once more. So this is some kind of chaining of free encryption with a little bit of care to take due to the fact that an encryption is just a pair of group. Okay, so this is some kind of triple L-gamma, and decryption is just the easy thing that you have to do, reversing the operation. Still, there are some problems due to the fact that the groups are not the same with not the same prime. So you really need to impose something like P1 less than P2 less than P3 so that you don't lose information. And this is indeed enforced in the source code. But all what I described here is just from the source code. There were no documentation, nothing describing or analyzing this anywhere. And but if you start to analyze it, the security is actually very poor because unless, contrary to triple S, actually you don't really increase the security. The security is just multiplied by 3. You have to just break the 3 L-gamma independently, and that's it. So basically, this didn't add any security to have these 3 primes, and I think that they explained that having 3 primes of 256 bits were enough to have a security equivalent to 768 bit, but no, of course not. And why did they do that? So as I said, probably they wanted to emulate 768 bit, but why not taking 768 bit prime? And in the source code, we can find a line talking about this solidity max int, which is indeed a constant of 256 bits, and the P should be less than that, modulus P. And if you don't know, solidity is just the name of the programming language for smart contract in Ethereum. And actually, there is some code in Solidity, so some smart contract code used to decrypt the ballots in the source code. So the idea was probably that in this Solidity, the limit is 256 bit, and they didn't have time, maybe they didn't have the competence, they didn't want to write a multi-precision library, and they decided to try to increase the security in another way. So my guess is that everything is just due to this blockchain that they used for the smart contract. Coming back to 256-bit DLP, well, actually this is easy. So make a long story short, takes a few minutes to break the discrete log in such a prime. Of course, you have 3 keys to break, but this can be done in parallel. And when I say a few minutes, it's just standard hardware, nothing fancy here. And in the challenge, for the public testing, there was some kind of limit of 12 hours. So the breaking should be done in less than 12 hours. And of course, we were more like 12 minutes. So it was broken. What they did after I said this to them, and I advertised a bit so that they really have to change it. They updated the source code, so triple L-gamma went away, and they changed the protocol. So actually, the decryption is no longer a part of a smart contract, and then they could increase the key size to 1024 bits. And at the same time, they also took into account a small remark I did, like, oh, by the way, you should take the generator in a prime order subgroup, otherwise you might have some small subgroup attack. And that's what they did. Unfortunately, shortly after, maybe 2 days after, Alexander Golovnev realized that they actually didn't map the messages into the subgroup. So actually 1 bit is leaked by the ciphertext. Ciphertext tells you whether or not the message is a quadratic residue, and the message is just the ID of the candidate you are voting for in the setting of this voting scheme. So actually you get, if you have only 2 candidates, or if you know that there are 2 main candidates, one of them having a quadratic residue as an ID on the other one, then basically you know you know everything. So this is very bad. But it was coming very close to the end of the testing. The election was approaching, and it became very chaotic. First, they denied that there was a problem, then they silently fixed the code, then finally made it public. But 2 days thereafter, it was really weird. Anyway, it was fixed, and in the end, I guess the encryption was okay. Okay, 1024 bits is certainly too small, and there is no hint about where the primes come, so there could be some hidden trap, but well. This is actually not the main problem in the general system. So there is no specification and no documentation. So what I say is just based on speculation, discussion, press article, and a bit of source code. But the general impression is that everything is bad. There is essentially no privacy due to this weak encryption. Verifiability is very partial despite the use of these blockchain things that actually, blockchain is usually, when you say blockchain, it's for people to be able to verify that there are things in there, but we'll see in a minute. It's not at all clear. There is no provision for coercion resistance or vote buying, which is very bad, again, in this weird context that they had. So, furthermore, there is a problem with the blockchain. It's a private one, so it gives you essentially no guarantee compared to a basic bulletin board maintained by an authority. In fact, it's even worse because shortly after the tally, after the result was proclaimed, the access to the blockchain was cut. So it really proves that it's not really like a permanent ledger or whatever. They were able to cut the access. So it's amazing. Yeah, this is so. At that point, usually I should basically conclude about what we had a lesson learned, blah blah blah. But actually, let's talk about 1 year later. Just a few weeks ago, we had another election in Russia. And it was even more important. It was the constitutional amendment. It was some kind of referendum for all over Russia. And it was just beginning of July, if you remember. And this time, again, internet voting was possible. And even more, it was possible for all the residents of Moscow and from the region of Nizhny Novgorod. And again, they had to register in advance and so on, but it was kind of the same setting. And the system used has also been designed by the same department, so it's probably more or less the same, but this time the code was not public anymore. And it was said that they changed the encryption to use elliptic curve via the lead sodium library, which is a good idea. And also they used the Exonym blockchain. So Exonym is kind of framework for private blockchain. So it seems that they stick to private blockchain, but there is no documentation. I asked again, but I could not get any specification documentation about what's going on with this system. And this time I had no real time to work on it, so I don't know much. And without the code being public, I guess it becomes a bit fancy to try to get some information. I mean, without speaking Russian, it's quite difficult for me, I guess, to get more information without the code. Anyway, so there is basically nothing to report about this e-voting system. Still, we can say that it was massive. I mean, the use of internet voting was massive, maybe to the pandemic. In Moscow, 1 million e-ballots, and in Nizhny Novgorod, more than 100,000 e-ballots were cast. So for the total that I give here, as you can see, it's more than 1% of the ballots that were electronic, and in Moscow, it was more than 20%. So really, it's increasing this use of internet voting. And apart from this point, we can really say that there were some accusations of fraud and coercion. Most of them were not on the voting part, actually. So I've given a link here. There were, but this is one among other that gives statistical evidence of ballot stuffing. And this is a bit amazing, actually. I really recommend that you have a look at that. It's wow. But there were also some reports of coercion, and this time a bit about on the e-voting part, like, yeah, you should register. So yeah, again, not at all peaceful context. So what to conclude about all this story? 1 year ago on this recent story, I guess the first thing is that internet voting in Russia is still far from satisfying in terms of techniques. No public documentation is available. The usual properties, privacy, verifiability are not really guaranteed. And there is no coercion resistance that I checked. And this is a context where you do want coercion resistance, for sure. And so we end up with this question. I mean, since we have heard about also frauds and coercion in the real polling station, physical polling station, then I mean, you know, usually my position about internet voting is that, okay, don't do it for high-stake election. It's difficult to make it good. Coercion resistance is pretty hard to get. So better stick to something that works, namely physical polling station. But here we are in a situation where even police stations don't work. So I really don't know if we should or not recommend to continue these experiments with electronic voting, maybe trying to push them to get something better, verifiable, and so on. So yeah, I guess this concludes my talk and opens more discussion, I guess.
Okay, so we'll thank Pierrick, and we'll start with the questions. Again, if you want to write them, it's preferable to do it in the ICR chat room. We have a first question from Josh Benolo, and I quote, "Even with all of the catastrophic properties of these systems, I'm surprised that you're not more critical of the use of blockchains, which would seem to immediately disqualify any voting system. You've mentioned some of the attacks enabled by the use of blockchain. Do you see any benefits at all that could not be better achieved by other means?"
Okay. Blockchain and e-voting, yeah, this is a typical questions. And okay, my opinion is that maybe a blockchain is a reasonable way to implement a public bulletin board. When you want to make all the encrypted ballots public, you might get guarantees that this is really permanent and so on and so on. But I mean, you could implement this also with some kind of consensus algorithm. But well, maybe using a blockchain here is possible, and maybe it gives something. My main problem with this blockchains and e-voting is that I mean, what we've seen in the past few years is that when there is someone proposing an e-voting system based on blockchain, usually this is so bad because blockchains gives a false impression of high security. I mean, blockchains are not for privacy. They are not for, I mean, they give you a bit of verifiability, but you have so many properties that you need in e-voting. I mean, just don't believe that blockchain solve them all. They can just solve maybe a bit of verifiability. That's it. So I guess, yeah, I agree with Josh. I mean, if you hear about e-voting with blockchains, usually, I mean, just from the start, assume that this is bad. This is a good bet.
Okay, thank you. I have another question. There are a lot of security experts that says that we simply shouldn't have electronic e-voting. For example, Matt Blaze and there are other very strong advocates against it. Do you also think that this is a lost cause, or do you think that there is a potential to do it in a safe and private way?
I think that we are not ready. The state of the art is not yet satisfactory for high-stake elections. internet voting should not be done. Unless in this weird context, as I said, where even the other classical election doesn't work, then so I don't know. But if you replace something that works by internet voting, just don't do it for a high-stake election. But there are also many cases where the stakes are not so high, or maybe anyway there is no other option than postal voting. I mean, if remote voting has to be done, then maybe internet voting is not worse or can even be better than other solutions. So there is no simple answer like never do internet voting. I mean, you should compare to what exists and what you replace. That's the thing. And but if you want to replace voting at polling station where you have, for instance, coercion resistance that is not so hard to implement, then don't do internet voting. Then coercion resistance, for instance, is pretty hard to get in practice for internet voting. That's,
okay, thank you. Maybe a final question. There has been a lot of examples where security experts trying to look at government products for security, if it's elections or more recently contact tracing, that have received a lot of pushback, either from private people or from the governments. Did you encounter anything like this when you looked at the system in Russia?
What do you mean? So sorry, what do you mean by pushbacks?
Either by saying that this is illegal to do, or that or something like that.
So this, due to the fact that it was a public testing, it was not illegal. but I got some kind of weird impression from time to time. It was very difficult for me to understand what was going on, because some communication were via the press written in Russia, and it just, for instance, I learned, so there was some bounty program on the, I earned part of the bounty, but I heard about this in the press. They didn't tell me directly, but in the press written in Russia. So in that case, I mean, so there was no really pressure or whatever that I couldn't really understand, because just I had a lot of difficulties to communicate with them. So it was really, really weird, actually, this situation. And also I've been told later that in the Russian press, they were attributing to me some things that I never said, like they said that I was impressed by the quality of the system or something like that. So it seems that they were doing their stuff in Russia and then having the rest of the world, the communication with the rest of the world, which was different. That's how it is.
Okay, so we'll thank the speaker once more.
Thank you very much.
Thank you very much. And we'll head off to the next session. Matej?
Yes. So our next session will be the keynote of this workshop. And we are very glad that Elisabeth Oswald has agreed to give a presentation at this workshop. And her talk is titled "Towards a Reliable Methodology for Creating Leakage-Resilient Software Implementations." So let me try to share the video again. Okay. So that should now be showing. We can maybe wait a few more seconds to see if there are several people still joining for the talk. The number of attendees seems stable, so I'll hand off the word to Elisabeth.
Hello, my name is Elisabeth Oswald, and I was asked by the organizers of the workshop on attacks in cryptography to give an invited talk. So this is what this video is for, and I plan to talk about the ideas that I have developed together with my colleagues and researchers to create perhaps some tools and the methodology that will result in leakage-resilient software implementations. My current affiliation is with the AAU, that stands for Alpe Adria University in Klagenfurt, which is sort of my home patch in Austria. And I still hold an affiliation with the university most of you would probably associate me with. That's the University of Bristol in the UK. And the research that I'm talking about is largely funded by the European Commission via the ERC. So what I hope you will get out of this talk is perhaps a better appreciation and understanding of why there is such a considerable gap between what we do in the kind of academic crypto field when it comes to proving algorithms secure with regards to various types of leakage and then the actual practice. So maybe some of you would be a bit more critical anyway when it comes to provable security, and for you it mightn't be so unsurprising that many schemes that have been proven to be secure with regards to certain leakage properties are in fact, when you take them and faithfully implement them, most likely not secure on an arbitrary platform. But the perhaps more interesting question is, why are we struggling so much to kind of narrow this gap, or to just find ways to deal with the fact that a proof is more a mathematical idea rather than a practical reality, and nevertheless put this into practice? So in my opinion, this has a lot to do with how we capture or model leakage. And I'd like to simply try and explain to you some of the models that we use and how they perhaps fall short of what is really going on in reality. And I'd also like to kind of argue that perhaps it's not even particularly meaningful to try and model things in such a way that it captures all reality of a specific device. So perhaps the mismatch between theory and practice isn't the real problem, but the real problem may be that we lack the tools to kind of understand and work with the gap that we necessarily create. And then nevertheless try and find interesting ways of taking some of the provably secure schemes and put them in a device such that many of these provable secure properties kind of are retained. And I think this kind of struggle where you try and understand theory and try and kind of somehow get it to practice is actually really cool and exciting. At least it is for me and people who work with me. So first of all, to warm us all up, I'd like to just reflect a little bit on leakage itself and how it matters. So in the early days, so around 1996, when the timing attack paper was published and very shortly after the power analysis paper followed, this really sent shockwaves through the crypto community, but also through the industrial community. And you may realize from kind of the chain of events, this also sparked off, I would say, the growth of the entire chess community, which is now really big within crypto and well appreciated both by academia and industry. And a lot of work then immediately happened around side channel attacks or leakage attacks. And in principle, leakage can be of different forms and it can be used for different purposes. So I'm not a big fan of having big kind of tables where you kind of try to characterize different types of leakage attacks. Yes, there are some where clearly the leakage is because of how a specific device is built, so it is about the hardware. But often leakage has got many different roots. So it's not just the hardware, it's also the software. It might be also how something is used. So leakage can be of many forms. Power, timing, EM are the classical side channels, but error messages are also very useful. Sometimes you can induce specific types of leakage by faulting a device. So you see there's a crossover between these potential categories of attacks. You can utilize different properties of TCP connections, for instance. So there's also protocol level leakage. And so there's all kinds of stuff out there. And you can use this leakage for different purposes, as I said. Typically in the crypto community, we use it to actually reveal key information. And we typically go for entire key recovery, which is perhaps not the most representative attack, because certainly from a crypto point of view, you don't consider a scheme broken only when you're able to recover the full key. Typically, our security notions are much more subtle. And for instance, indistinguishability has nothing to do with key recovery. It's a much stronger notion, much more useful in practice. And as you may kind of know, as most of the leakage attacks that we consider practical recover entire keys, you can imagine that indistinguishability in the presence of leakage becomes basically impossible. So what's the role of hardware and software in all of this? So traditionally, secure hardware was advocated as a kind of secure key storage. The idea was that you would have a piece of hardware with a very limited interface, so that if you put your keys in there, then they would remain in there securely, because you couldn't simply ask the device to return the key. But of course, with side channels, this is all not so true anymore. And then we have got these kind of software solutions, which also hyped over the last years. Things like SGX or ARM Trust Zone and things like that. So here, this isn't really about secure hardware. This is just about the software layer, which again was advocated that it would keep certain things in certain compartments of a chip and therefore would be more secure. But none of these software solutions has ever been designed with side channels in mind. So really, we should never ever expect them to give us any form of security with regards to side channels. So from the academic perspective, leakage also still matters. Obviously, at the very beginning of side channels, there were huge numbers of papers being churned out every year. This has perhaps slightly decreased, but not very much. And if you Google for power analysis attacks, as I have done when I prepared this talk, then you currently get about 3.3 million results. So, I mean, this is a staggering number of papers. Obviously, there will be duplicates and so on, but I really just Googled for power analysis attacks. So this won't include things that have timing in the title, or that just come with a title that says something about leakage resilient or EM attacks. So there is really a staggering number of works out there. And it's been so popular that there was even a panel discussion that dealt purely with leakage. And I would like to kind of use this as part of my talk. So let me turn this video on and we'll listen to it for a little while.
Okay, so next up is a panel. The panel chair is going to be Dan Bernstein on the podium microphone, and the panelists are Ian Goldberg from University of Waterloo, Moti Young, and Kevin McCauley. And the topic of the panel is leakage.
Leakage. Leakage, 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 leakage.
I'm sure you will have found this summary about the status quo really illuminating. And for those of you who couldn't quite follow, because the sound is not great, I shall kind of provide a little translation. So how do you then deal with leakage in software implementations? So in principle, strategies like masking, which is the kind of side channel terminology for secret sharing, and hiding, which largely means random rearranging of code sequences or inserting dummy code sequences, we know how they kind of impact on leakage. This is very predictable, and when we can describe things, I would say in reasonably good ways mathematically. So it's not that we don't understand how these things act, but it's more that often the world is slightly more complex than we would like it to be when we make these arguments. So when it comes, for instance, to masking, which will be sort of the running example that I'm going to use for some of the attacks that I'm going to show you. So it kind of means that we take an intermediate value. So maybe this is the plain text. Maybe this is the key. Often it's both of these variables. And we ensure that it's not represented as a single value, but we share it out into multiple shares. And if we, for instance, have 3 shares, then we call this a order 3 masking scheme. So the idea is we share things out, and then we hope that leakage only occurs on the individual shares, but not on all of them jointly, such that we can't really make much sense of the leakage of the individual shares. So as we know, if there were such an involuntary recombination of all shares happening, then of course we would be leaking information. So one of the criteria when you kind of devise a masking scheme, when you actually write this down algorithmically, is that you ensure that in no step all the shares ever come together. The way in which you do that is typically in our community by providing a sort of higher level pseudocode description of an algorithm. So you try and specify as much as you can how every single step in your algorithm works, in the sense that which variables are being taken and what is the output. And this is really, the intention is really to define the exact ordering of things. And then with such a description, and based on a range of assumptions about leakage, and we call this leakage models, you can then make certain proof statements. And typically what we try to show is that none of the things that matter, none of the intermediates that matter are ever really revealed. So this brings me to the topic that I find particularly fascinating, and this is the topic of leakage models. What is that? So let's have a little bit more input from our panel discussion.
Leakage?
Leakage, 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 leakage.
Very illuminating. And I will try and translate for those of you who couldn't quite follow because of the bad sound quality. So there are many, many different leakage models, some of which are very discrete, some of which are very continuous. Sometimes we know them because we have actually examined the device, and some are purely made up. So when it comes to really discrete leakage models, we, for instance, very often in the literature find what I would call a linear bit leakage model. So something like the Hamming weight. So we sum up, we have a function, we assume the leakage is a function, a linear function of the individual bits within a variable. And maybe they are weighted, but largely it's sort of the Hamming weight. And this kind of leads us directly to a loved model for proof techniques, or for proofs, which is the probing model. So here we assume that an adversary can put a number of probes on a circuit, which means that they can simply learn the value of certain bits. There is a more general version of this, which is called the noisy leakage model. So here we again allow the adversary to put probes on a circuit, so they learn certain bits, but only with some probability. So sometimes they learn the bit and sometimes they learn nothing. And there are all sorts of variations of that. And the interesting bit about these models is not that they represent reality, they really don't, but it's kind of been shown in the literature that for these variations, if you actually make a proof in a probing model, then this typically translates to the other more noisy leakage models. And the probing model is something that perhaps we understand very well, and we can do lots of proofs in them. So all of the masking schemes that we know for symmetric encryption, they're always basically proven in a probing model. But that's not massively realistic, because just having independent bit leakages is not very representative of real devices. So there you find typically interactions between bits. These might be interactions between subsequent instructions, and then we would find this as so-called Hamming distance leakages in the academic literature. Often there's the assumption that this is only between sort of neighboring instructions, but this is not true. Variables remain for quite a while in a processor, and so Hamming distance interactions can occur between variables that are sort of far apart in a program code. But it's also that people have observed that neighboring bits kind of leak jointly, or that there are more complex interactions, in particular when it comes to implementations of complicated functions, so S-boxes in combinational logic. Then we know that the leakage from these tiny components in hardware is a highly nonlinear function in the input or output. And then there is another sort of theoretical model that really makes sense in the context of typical side channels, which is the so-called leakage resilient model. And here the idea is that you're not trying to actually give a functional description of the leakage, but instead you just say it's any efficiently computable function for as long as it's somehow bounded, so that if I invoke it, I don't get the entire key out. if that really happens, then there is no hope anyway. But if I don't get the entire key out, then perhaps I can do something. I can come up with a scheme and can prove something in terms of its security. And when it comes to now sort of practical use of these kind of things, then perhaps the leakage resilient model, so that's my favorite. I think it's in a way conservative in the sense that it doesn't make any assumption about the functional form, and you can still work with it. But the schemes that we have found, unfortunately, so far, they're all, I would say, a bit too heavy to really work in practice. The kind of scheme, the leakage model that is used in most papers is related to the probing model. And as I said, any sort of masking scheme typically gets proven in this model, although it really isn't particularly realistic. There is another sort of implicit problem in the assumption that a device has a leakage model, and I'd like to illustrate that on my next slide. And this is the assumption that if you have a device, then this device follows a single leakage model. So this isn't true. A single device has many, many different leakage models. And in fact, even a single instruction on a device does not always leak in the same way. And I have no better way to kind of illustrate that than to simply show you some power traces from an instruction, which changes considerably depending on which instructions surround it. So here what you see on the slide, and I will use my cursor to kind of guide your eye. So what is really leaking here is the exclusive OR instruction, a well-used instruction for many symmetric encryption schemes. And what I've done here is I have surrounded this XOR instruction with something else. So a load in the case of the figure here on the left, and a shift operation on the right. What I've also done is I have taken multiple data samples, I've averaged them to make them look nice, and then I have kind of color-coded them according to the Hamming weight of the data that has been processed here by the XOR. And what we can see here in the picture on the left is that we have got 9 traces. They are not exactly equidistant, but they are properly ordered and they are somewhat spaced out. And they're ordered from low Hamming weight to high Hamming weight. So what you would say here is, and maybe I should guide your eye to that as well. So we see here that we have this kind of relationship across this kind of stretch of a power trace or curve. And this whole curve represents sort of a clock cycle. So it's not so much this overall big shape that I'm after, it's really just the relative differences between the different curves here that I'm interested in. So this relative difference here, kind of, it follows a linear function more or less. And here you would really argue, okay, that the leakage here of this exclusive OR is largely governed by the Hamming weight of the value that is being XORed. Whereas if we look here on the right-hand side, where the XOR is surrounded by a shift instruction on a processor, and I'm going to eventually say some more about the processor, then this looks rather different. Not the whole curve. I mean, this is just, again, a clock cycle. This is how a clock cycle looks like in our setup in this device. But I'm drawing your attention to the individual curves that I have, again, color-coded according to the Hamming weights. And we see some ordering here, but it's clearly not as linearly spaced as it was in the curve on the left-hand side. And if you build a functional model for that, then you will see that for this particular instruction sequence, the functional form of the leakage looks actually quite different to the leakage here on the left-hand side. So the point I'm trying to make is devices don't have a single power model, not even an instruction has got a single power model. Any instruction and its leakage will depend on the entire state of the processor, and that depends on what happened before, at least one instruction, but probably more depending on the pipeline length, and then also what happens afterwards. So the next problem then that we have identified with this kind of whole assumption around leakage models is that just having one in a proof makes no sense either. I'd like to spend another slide on reflecting on the consequences of using a wrong model. So it's not just that we kind of make a small mistake, we can actually make really large mistakes when we use wrong models. So in many papers, when researchers, whether they are now academics or industrialists, doesn't matter, attack an implementation, and they will make this assumption that the device largely leaks the Hamming weight. So the Hamming weight is a good model, and so they will run a correlation attack with the Hamming weight. If we do that on the same device that I used before to generate the traces, for again an implementation of a symmetric encryption scheme, and if we print the curve, the attack curve that corresponds to the correct key guess, then we'd see something like this. So this curve here indicates a low correlation for most trace points, and then suddenly some higher correlations for some of the trace points. And in the side channel community, whenever we see peaks, we get excited. A peak normally means, okay, there is some form of leakage. So if we use the Hamming weight model with this device, we can see, okay, there are problems in the code sequence that has been executed. But as I mentioned, even for this simple device, perhaps, a single power model is just not adequate. So what if we were to use the correct power model for every instruction here? And I call this here Elmo generated model, and I will say a little bit more about Elmo in a little while. So if we use for each instruction the right model, then actually we see suddenly that there are many more peaks. So there are some peaks which we have identified before, but there are also peaks which really weren't showing in this curve here above. So we would have completely missed out that here there is some data dependencies that will reveal the key. So we don't just make small minor problems. So it's not just that our attacks require more traces. We will actually miss out entire attack vectors if we're using the wrong model. Because every peak represents a vulnerability, and it might be a unique vulnerability. So solving the problem here mightn't imply that we've also solved the problem that is somewhere in here, but we can't see it with that power model. So having a good understanding of how a device leaks really is fundamental to get anything securely implemented on a device. And I guess this leads us very quickly to the question of what is then a realistic model and how do I get them? So this is a really tricky question because realistic models entirely depend on how processors are being built. The processors that so myself and my researchers are mainly familiar with at the moment are processors of the so-called ARM Cortex-M family. So this is a specific type of architecture. So there's an M0, there's an M3, there's an M4. They are slightly different in how the architecture is defined. And for instance, if we look at the M0 and M3, then these devices feature a shifter as part of the data path. So this component, this shifter, is always on. There's always some data in it. It's always shifting. And perhaps the software developer, we just don't know that this is happening. And shifting means that we are moving data around within a register. And the way in which shifters are typically implemented are by the so-called barrel shifter implementation. So you've got multiple multiplexers, multiple shift units. And so depending on what kind of shift you need, several of these kind of components in the barrel shifter will be active, and then things will be kind of moved through, and eventually you've got the correctly shifted data output here at the end. So this thing is always on. It has got several layers of circuitry. So there are many so-called glitches in between. That means circuits that keep toggling until they have stabilized. There are also kind of little buses in between. So we've got bus transitions. And I think it should be absolutely clear that a bit linear leakage model makes no sense here for this component. There must be some interactions between variables. And without including them explicitly in a model and in a proof, no provably secure masking scheme can be practically secure on such a device. So more consequences of wrong models. I've already given you one. This is that we simply miss out problems. But there can be more issues. So here, for instance, another interesting scheme to consider is BDF from 17. And so this is Barte et al. And here the idea is that on modern processors, so this includes again the ARM-M family, it's a real pain to implement masking because it's, masking has a lot of overhead, it's very slow. So could we not find a way to make things more efficient by sort of parallelizing masking And you can parallelize things in software by slicing variables in a different way, such that you pack things that occur in different shares into one variable, and then you can perhaps do more efficient operations on them. And they wondered if that could actually work in a leakage resilient setting. And so what they show is that basically if you can prove a serial implementation of an oath order masking scheme secure in the probing model, then under certain independence assumptions, you can also prove a parallel implementation secure in the bounded moment model. And this is related in terms of the security assumptions. Here the idea is that you only care about leakage up to a certain moment. So with all of this in mind, they then come up with a different description of an AND implementation. And again, I just write down the simplistic 2-share version here so that you get an idea of what is actually being executed. So you've got here the 2 shares of the AND result, and this is how you can recover the original value. So what happens if you implement that faithfully? So let's just think again about the proof assumptions or statements that will come together here. So sequential leaks, so if we implement things in sequence step by step, then security at order D means that no combination of fewer than D leakage points should provide information about the intermediate. This is what we hope to achieve by D order masking scheme. If we've got parallel leaks, then what we are expecting is that security at order D implies that if I take a single point and raise it to a power lower than D, I should again see no leakage. And at order D, what we would expect is that an attack at order D must succeed, because this means recombining all of the D shares. But doing such an attack should require many, many more traces than an attack on the unprotected scheme. Okay? So let's have a look then at what happens if we implement this BDM masking scheme on our M family of processes. So in theory, what we would expect is that higher order leaks should require more traces to detect them. In theory, we shouldn't in fact detect any leakage at an order lower than the security order. What happens though that in practice we detected leaks at all orders, and higher order leaks were not always necessarily harder to detect. And you can wonder why. Is this because we made a mistake? Or is there a problem with the proof? And it's neither. The problem is, again, in the assumptions. And the assumptions are all about linearity between variables, between bits, and this is simply not fulfilled by the processor. And it is down to this particular element that I've pointed out before, which is the barrel shifter, which is always on. So it's always active, it has always got some data in it, and it will inevitably produce complex interactions between bits within a data word. And in the case of share slicing, this means it produces nonlinear interactions between bits within a share. And then coming to concrete attacks on the BDM scheme, now here there's a version with 4 shares. And again, we've got here something that relates to a shifting operation. What we can see is that if we have got 4 shares, the first order attack will already work. So first order leakage detection shows that there are leakages. Second order, again, third order, we haven't printed. Fourth order, again, so we would expect something at the 4th order. Perhaps what is interesting is that, in theory, there shouldn't be anything below order 4, but what is particularly devastating in this case is that here the second order attack actually is slightly more efficient than the 4th order attack. So in principle there shouldn't be anything lower than the 4th order, but we find something and it is more efficient than the 4th order attack. So this means really that anything that the masking scheme tried to achieve essentially falls down. And it's not just that the masking scheme is problematic, it's that it simply doesn't fit to the reality of the ARM M0 and M3 architecture. And the problem in here is that there is this shifter which is always on, and there's no way to mitigate against this. this shifter will be doing its job, whether it suits us, cryptographers, or not, which means that basically there is no way of implementing share slicing on this processor securely. A way forward, are we simply stuck with this? Well, to some extent, yes, because certain processors with certain architectures are simply the way they are. They will not change based on our demands. But perhaps what we can do is we can help people who have to implement things in software do not fall into these traps and then scratch their heads and wonder what in Earth's sake is going on. Maybe we can make the world a bit more predictable and obvious to them. So what I hope by now is that I've convinced you that the leakage of modern processors really does not support these bit linear leakage models, and strict independence assumptions between bits or processor words, variables, registers, however you call it, they are also not easy to fulfill in practice. So somehow we need to be able to tolerate interactions in reality, and that even go potentially across multiple clock cycles. And we need to really know where they occur. So in other words, we need an accurate model of leakage characteristics of processors that we're interested in. So one of the things that we have done is now a few years ago, but this still sort of drives much of our research, is to kind of really consider how do we best model the power consumption or EM or whatever of a device, and how do we make this available to developers. And this isn't necessarily perhaps a completely novel question. So if you are in the side channel community, you will be, I'm sure, aware of the various works and papers around templating. So templating has been on the cards ever since the very first paper about power analysis attacks, which suggested characterization and called this templating. So in our jargon, templating, in theory, refers to building fully interactive models between some specific variables. So if we go to our sort of simple example that everyone uses in the community, we consider an S-box, whatever shape or form, maybe these subbytes from AES, then we'd need to decide whether we believe that the leakage of this of an instruction that corresponds to subbytes only depends on the input data, or if it depends on more than that. And typically what people do in the literature is they say, well, okay, we build actually templates only for already an assumed power model on the inputs of subbytes. So typically it's people build 9 models, so the Hamming weight of each input for subbytes. Whereas actually, if we really do templating as it perhaps was intended, then we would need to think, okay, perhaps because the XOR happens just before subbytes in the first rounds, actually the power consumption will depend on both the plaintext and the key, and we don't want to assume a power model. So actually we would want to build models for 256 square combinations of inputs. And the reason why people gravitate to the simpler models is just because the more complex models are very data hungry. So you need to sample lots of device data to actually have a good estimation for the model. So in principle, templating could give us what we want, but because it's so data hungry, nobody's really doing it. On the other hand, what we have in the literature is what people call, interestingly, linear regression. And typically this doesn't really mean using just linear regression, it actually means more, namely that only the linear bits of a leakage model are really models. So you kind of make, again, a bit linear model, and you essentially estimate the terms from the data via linear regression. Now, what our contribution was a few years back, and our, I would say, big realization, is that there is actually something in between from the statistical literature. And this is what other people would call statistical model building. And here the idea is that you do not assume already a priori a functional model for your leakage characteristics. So you're not saying it is fully interactive or it only consists of linear terms. You're actually saying, well, I would like to know what terms should I include. And I'm going to ask this question in a statistical manner. And I'm going to use statistics and the observed data of my device to decide whether certain terms should be included or not. In that way, we can strike perhaps a balance between the complexity in the model and the amount of data that we need to estimate it properly. And this looks a little bit like stepwise linear regression, but it really isn't for those who are a bit more into it. So we proposed the methodology in that Usenix paper that consists of certain statistical tools and then also certain ways of actually dealing with the data. So we've done this for different devices that follow an ARM architecture. And this is often a bit confusing when I'm using sometimes the words ARM device and ARM M0 and ARM architecture interchangeably. So I'm going to make an effort to clarify this before I move on. So ARM is a company that produces architectural descriptions of processors. So they are responsible for the processor architecture and for the instruction set of the corresponding device. But they do not manufacture. Instead, other companies, like for instance SD or NXP or many others, they license the IP from ARM, and they are then responsible for taking this architectural description and actually turning it into a real processor. So one thing to really bear in mind is then that an M0, so a processor that follows the M0 architecture, that is implemented and fabricated by company X, maybe ST, is different to a device that implements the M0 architecture from company Y, maybe NXP. So what we cannot assume is that we can just produce a characterization that will work for absolutely every M0. But we did do that in our work. We actually had a look at differences, and you can, in part, by looking at the power models that we have derived, you can sort of in part reverse engineer the differences in the M0 implementation from the two companies. Another thing to bear in mind is that this architectural description defines the CPU, but there is also access required to external memory, and that's gathered by a different specification. There's some bus in between. Typically it's the Amber bus. And again, this kind of is an architectural specification, and how it is implemented depends on the vendor. And so it's absolutely possible that the Amber implementation of SD is different to the Amber implementation of NXP. So it's not really fair or possible to say, well, I will make a model description for the Amber bus. But what you can do, and again what we did, is you can kind of characterize a device, and then perhaps, or sometimes you can sort of reverse engineer a little bit how the different implementations of the architecture has been done by different companies. So another thing I'd like to say before moving on is that we do not have the actual ARM architectural description for any of the processors that we analyze. So when it comes to ARM, we really work in a black box setting completely. So the model building, when we do it, it requires quite a lot of side channel expertise. It requires a lot of statistical expertise. And we have to proceed in multiple stages because we have to every now and then second guess results and perhaps go back and try other things. So when we go model building, what we do is we first build a basic model, which means that we actually ditch any idea of interactions and complicated leakage. We just build basically a very linear model for instructions, and then what we use that for is to just see if we perhaps can cluster instructions. And the reason why we need this is that, remember I said that any instruction, it doesn't have the same leakage all the time. It depends on what happens before and after. So if we want to build a really accurate model for a processor, we can't just go and characterize each instruction individually. We have to in fact decide on a kind of window of an instruction sequence that we will have to dispatch, and then among these, I don't know, 3, 4, 5 instructions, there will be our target. And we build a model for the target, but we surround it by other instructions to kind of trigger the processor to kind of perform its natural behavior and leak in all sorts of ways that we then try and capture and characterize. So for the ARM, we, with lots of experiments, kind of settled on using sequences of length 3, and the target instruction is in the middle. The models that we build only take as variable input the first 2 instructions, but because we have a third instruction going on in the processor, we kind of get the leakage, the impact of that third instruction as part of our models. So we do this, as I said, we start with a basic model that's sort of treating all the instructions independently, and we do that only to group instructions. And then we end up typically with a set of classes of instructions that's much smaller than the overall number of instructions. And then we can sort of dispatch instruction sequences where we put together instructions from different groups. And this then gives us kind of the ability to deal with the otherwise way too large number of instructions and combinations that we would have to consider if we wanted to kind of model all instruction sequences of length 3. And for these kind of combinations, then we do check which nonlinear terms make sense, and we include them in the model. I'm not going to write down the kind of the functional form of the model that you get. You can read this up in our papers. Instead, I'm just going to sort of talk a little bit about what do you do then with these models. So we've integrated these in instruction set emulators, and we developed 2 kind of tools. One is called Elmo and one is called Giles. Elmo was our very first prototype, and my back then student David put an enormous amount of effort into getting this working. Later on, my colleague C has added a module that kind of gives you some indication of the bus leakage that's there. Elmo can also do sort of, it helps you with setting up leakage detection statistically correctly. It has all sorts of little tools that help you to track leakage and to fix leakage. And then Giles is our second prototype. This one has been much more modular. And Giles also can do fault attacks, and it will flag timing variations as well. We've modeled very many instructions from the ARM instruction set, but not all. So there are things missing. And we know for the models that we have built that we are not yet capturing all of the data-dependent variants. We don't intend to capture all of it either, but we know that we are missing something that's perhaps significant. And we are thinking about ways in which we could make them more accurate. We also know that the models are good enough to do energy predictions, so that's quite cool. And so we have got a number of sort of further on questions and activities currently going on to kind of deal with our missing out on certain perhaps relevant interactions. But by and large, Elmo and Giles are doing very well in terms of helping us to find leaks in software. So here, for instance, is a graph that I show often when it comes to them. So what we have here at the bottom is a piece of code, and again, it relates to a protected AES implementation. And what you can see again is a leakage detection test, and the clock cycles, instruction cycles here actually that are indicated in red is where the detection test says, okay, you've got a problem, something's not right here with your masking scheme. And so this is sort of from a real implementation of that masking scheme on an M0, and this here is what Elmo predicts. So you can see that it will actually show you in the same clock cycles that you have an issue. So we capture the relevant leakage information. So what? So I'm coming to the end of my talk. It's kind of nice. So we are really fond of Elmo and Giles. They help with the semi-automated analysis of arbitrary code. I mean, one of the cool things about our methodology is that you are not sort of fixed to whatever fixed instruction sequences or so, what you typically get when you are templating in a naive way. You can run any piece of code through Elmo and it will output a reasonably accurate leakage description. It's also cool that, so we have got some tools already built in, but there is definitely much more that we could do. And in particular, the way in which we present models could potentially be useful to also do formal verification on the assembly level. And perhaps we could sort of take some of the workload off some of the formal verification tools that are out there, because our leakage models for the different instruction sequences tell you when proof assumptions are being violated. And one of our next steps is that so far we have worked pretty much exclusively in a black box context by considering ARM, M0, M3, M4. But with all of the buzz around RISC-V, it seems only natural to kind of branch out and look at RISC-V architectures. And that, of course, would mean working white box. So this brings up many more questions around leakage modeling, and how you give feedback to designers. Perhaps having cloud-based solutions for analysis tools. So all of this happens in collaboration with my now ex-colleagues in Bristol, so Dan Page in particular, where we are hoping to kind of do something useful for the RISC-V community. So what's the driving force behind all of that? Well, it's crypto for everybody. There is, I think, a lot of work going on in our community where we do crypto for crypto experts. And that, of course, makes sense. Academics talk to other academics most naturally. But crypto is such an applied topic. And crypto really has this hype because it's so necessary for the various products that will inevitably come into our lives, that I think we have a duty to make crypto more accessible to people who are not cryptographers. And crypto implementations are really, really difficult to get right in practice. And I'm not claiming that we are better or that we can really sort of help software developers quite easily, but perhaps we can give them something such that professional software developers are less stung by the various leakage problems that they will inevitably face in their work. And I really think that much more research is needed to facilitate secure implementations. And in particular, when you think about people who are not crypto experts. So as always, at the end of any of my talk, I do have open positions. If you're interested in leakage, if you're interested in attacks, if you're interested in kind of AI deep learning aspects of this topic, then please get in touch. I still have got posts to fill. And I wanted to say thanks again for the organizers for inviting me. This has all been funded by an ESC project. I've got a website, we've got our research on GitHub. Please come and visit, download, try things out. People have done, and it's always useful to see what people make of the kind of tools that we develop. Obviously, if you find problems, let us know. We are happy to fix things for you. And I wanted to finish with the end of that fascinating video and the panel discussion on leakage from Crypto 2011.
Leakage, 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 leakage,
leakage, leakage, leakage, leakage, leakage, leakage, leakage, leakage,
leakage, leakage, leakage, leakage, leakage, leakage, leakage, leakage, leakage, leakage, leakage, leakage.
Okay, let's thank the speaker for the talk. Thank you. So we already have one question on Zulip. So let me repeat the question. The question is from Dan Bernstein, and he is asking, do the power traces show differences in how strongly, for example, bit 0 times bit 16 is leaked compared to bit 0 times bit 1 in the Cortex M3 barrel shifter? If the shifter is organized as 16-8-4-2-1, then 0-16 would interact early in the clock cycle and 0-1 would interact much later.
So hello everyone. So my answer is only half-hearted answer, because the honest answer is I'm not quite sure. The more complicated version of I'm not quite sure is that the way in which we estimate the models gives us an indication of how strongly certain components leak, so how strongly certain bit interactions leak. That's also, we can see where roughly in that clock cycle it is. But what we haven't done is to really kind of zoom into this particular instruction and make a really great effort to determine this properly. So yes, but we don't quite know how strongly this manifests itself, but it does.
Okay, thank you. So there's another question now on Zoom. So is this also applicable to DEEs like SGX or Trust Zone?
So here again, the honest answer is I wouldn't know, because profiling this is something we have never ever looked at. I don't know whether we would be able to get measurements that are good enough to do the kind of analysis that we now do for the M series. So the honest answer is I don't know.
Okay, one more question from Dan Bernstein. So does the side channel modeling compared to observations help you deduce the pipeline structure on processors, where the pipeline structure is unknown?
So for the M series, we only know it's I mean, 3-stage. You know roughly how a 3-stage pipeline works. What we can see from how the leakage manifests itself is if there are, for instance, buffers in between. We've got a good idea of, for instance, how different the shifters are organized. We've got a good idea. So between different companies, we've got a good idea of how different the memory buses are accessed. So we can see a lot of detail. So you could do a lot of reverse engineering with our methodology, and we kind of keep track of architectural and microarchitectural differences in a GitHub repository, with the aim of, if we find enough interesting things, to eventually try and put this together into a paper that's kind of readable.
Okay, now another question from Akira Takahashi. I'm sorry if I mispronounced the name. So the question is, I see a lot of LR crypto papers only consider a single bounded leakage function for a particular sensitive value. For example, the signing key for signature schemes. Do you think this is realistic or valid assumption from a practical point of view?
So my understanding of the, when you say LR model, then for me this translates into the much broader class of leakage resilient papers according to, I don't know, Peter Schack's work. And there they say, well, there is a leakage function, but in every time an adversary uses that in their model, they can choose what leakage function it is. So it's not the same assumption as these kind of bit probing model papers, which kind of really fix a leakage function. In that other model, you just have this abstract concept that there will be leakage. This is bounded in some shape or form, but the adversary can, in every invocation, they can essentially issue a new request for a completely different looking function. So I don't think it falls under the same kind of problem that I've pointed out in my talk. If that's the one that the question refers to, then I would say this is not such an issue. If that paper was set up differently, then a single leakage function here makes no sense.
Okay, now a question I had. So I'm not too familiar with the domain, but I sort of have the impression that there's a cat and mouse game maybe between the model and the attacker, that you define a model, but then it turns out a certain attack is still possible. So I'm wondering whether it would also be useful that the processor provides certain guarantees. For example, that you can enter a special mode where you get some stronger guarantees from the processor to prevent leakage.
Yeah, the question is, how would you get the hardware to behave in the way that you want after you've built it? So, for instance, the problem that we see in the attack that I showed in my video is that there is just this shifter in the data path. Nobody thought it would be a problem. Certainly from many other aspects, it's perhaps a good thing that this is constantly on and going. Many parts of a circuit are not gated, so they are always on, they always produce leakage, because it would be too expensive to put little circuitry in to kind of turn it off if you don't need it. So unless you could make this happen where you say, I completely shut down parts of my circuitry, which I can't see how we would convince the circuit designers to do that. I just can't see how we would be able to do that. Of course, if you build perhaps your very special crypto CPU, which does not speculate for a start, which kind of is able to gate every single component that is currently not needed for the current instructions, that doesn't reorder your instructions as you issue them in your assembly code, then maybe these guarantees would mean something, yeah. But that would be quite an interesting thing to try and design and make efficient.
Yeah, okay, thank you for that answer. So far I don't see any new questions on Zulip on Zoom. So unless someone wants to ask directly on Zoom, you can unmute. Otherwise, I think we have covered all the questions. So let's thank you again for the talk.
Okay, thank you guys. Bye.
So the next session, so there's now a break, and the next session will start in about 40 minutes. So see you then.